Okay, for this next section, we're going to start some things that look a little different than Algebra 1. We are going to start some work on inductive reasoning and some logic rules. So before we get started with anything else, I need to tell you what inductive reasoning means. And it's the type of reasoning we use when we have specific examples. And we use specific examples to draw a conclusion. And that conclusion will be like our rule or our conclusion, I guess is what you would say. That concluding statement is called a conjecture. And the words in the book will ask you to write a conjecture for different examples. And I'm sure you guys have done this before. You've looked at patterns and you've been able to say, okay, the next number in the pattern is whatever. Like if you have 2, 4, 6, 8, you would say that the next number in the pattern is 10. You're using inductive reasoning for that because you're using a specific example and then you're making that conclusion. So looking down here, we want to make a conjecture about what is next in the sequence and also explain what that conjecture is. So I'm looking at these square numbers, the first number being 4. And 4 goes to 10 by adding 6. And then 10 goes to 18 by adding 8. And then 18 to 28, you add 10. So it's not that you're adding a specific number each time, but there is still a pattern with this because what's happening is you're adding 2 more than the previous number. So what you could say is you could say that the conjecture is you add 2 more than the previous number. And then it's going to ask you to come up with the next item in the sequence. So the next item, next number in the sequence would be 54. And that'll be the way the directions are. They won't always be, you're adding the same thing. They might be diagrams, but they're going to be asking you about what's happening for those. So sometimes they won't have an actual example out. Sometimes it might just say something like, we want to make a conjecture for the sum of 2 even numbers. So if you're not quite sure what that would be, what you could always do is you could make up some of your own examples. So sum, remember, means add, sum of 2 even numbers. You might choose 8 plus 14 equals 22. Or 2 plus 4 equals 6. Or 10 plus 20 equals 30. So we can come up with a bunch of specific examples. And then one thing that I notice is that all of these are even numbers. So the conjecture might be the result or the answer is even. Hi, boys.
How is actually playing Spider-Man 5?
That sounds like fun. So for this next one, it says we want to make a conjecture between the relationship between AB and EF if AB is equal to CD and CD is equal to EF. So again, you don't have any information other than this. What you're going to be doing is you're going to be coming up with a specific example and trying to make a rule based on that. So if I have line segment AB, and let's just pretend that AB is 7. And then I know that AB is equal to CD. So let's say over here I have CD. And again, I'm just making a specific example. So that would mean CD is 7 also. Yep. And then this last one says that CD is equal to EF. So if CD is equal to EF and CD is 7, then EF would also be 7. So based upon this specific example, I might make the conjecture that the relationship between AB and EF are equal. So I could say that AB is equal in length to EF. Okay? It's really hard to prove things that are true, but it's really easy to prove things are false because all you need to prove something is false is one counterexample. So a counterexample is one specific example that you can use to prove something is false. Used to prove a statement is false.
Wow.
And you might be able to hear my boys in the background. They're being kind of goofy right now. So these are some statements here, and I want to prove that they are not true by a counterexample. So this first one says that x squared is greater than x. Well, what that would mean is if you came up with an example that if you had, let's say, 4 squared, which is 16, is greater than 4. So this doesn't prove it false, it just proves it true. But proving something true, you can't just use one example. I need to come up with something that would prove that this is false. So a counterexample of this might be something like 1. If I have 1 squared, is that greater than 1? And the answer would be no, because that would be exactly equal to 1. So a counterexample could just be, the example is the number 1. And you really just need to come up with one example of that to prove that it's a false statement. Here's another example. Let's say if I have jk and equals kl, I want to prove, or I want to disprove, that k has to be the midpoint of jl. And I know that it could be. You know, if you think about this being like KL, or jk is the exact same length as kl, then yes, k would be the midpoint. But what you need to think here is you need to think of, is there any other way that this could be? Is there any other way that jk could equal kl, but k is not the midpoint? And yes, there are other ways. Maybe you have an equilateral triangle, and you have j, k, and l, and jk is equal to kl, and that could be a counterexample for that one. So really, you just need one specific way, and you would be all set. A picture would be a great way to show a counterexample.